Hi everyone, today I'm going to be talking about an efficient quantum parallel repetition theorem and applications. This is joint work with John Bostancy, Nicholas Spooner, and Henry Yuan. So to introduce the background, the theme of this work is going to be harness amplification. On a high level, the idea is that we're going to start with a weakly hard task, by which I mean that the optimal success probability of a bounded algorithm is, say, 3/4 or not much higher than 3/4. And the goal is to get a truly hard task, by which I mean that the algorithm that you consider cannot do much better than the trivial success probability. Let's say 1/2 or 0. So these include examples like amplifying a hard function, amplifying the indistinguishability of two distributions, amplifying the soundness of interactive proofs and systems, and also multi-prover interactive proof systems. This is a very widespread topic that can be found throughout TCS, and it has many applications such as proving circuit lower bounds, proving PCP theorems, and of course, the focus of today, which is cryptography. For this talk, we'll focus on one specific topic called security game. So in a security game, we have an adversary that is interacting with a challenger. In some context, these will also be referred to as a prover and a verifier. So they interact by sending each other messages, and at the end, the challenger is going to either declare the adversary has broken the security game or the adversary has failed to break the security game. So putting harness amplification into the context of security games, here we would have a weakly secure primitive against efficient adversary as our starting point, and in the end, we want to construct a fully secure primitive. So the optimal adversary success probability is essentially negligible. But that's not all. We also want to preserve all the desirable properties that the starting primitive has. So this includes time efficiency, round complexity, and for argument system, we also want to preserve zero knowledge. And there is a simple, natural, and very generic approach that at the same time satisfies all of these constraints, and that is the idea of doing a parallel repetition. This transformation is also sometimes known as direct product, by which I mean you just take the original protocol and then run manifolds in parallel. So you run independent execution for manifolds. And at the end, the adversary wins if the adversary is able to break all of these folds simultaneously. Okay, so before talking about quantum, which is the focus of this talk, let me first remind you what the classical landscape looked like for the question of efficient parallel repetition. So in the seminal work by Belair, Impagliazzo, and Naur, and subsequently improved by Canetti, Halevi, and Steiner, it was shown that if you have any three-message protocol with computational security epsilon, if you apply a k-fold parallel repetition to it, then the security will decrease exponentially down to epsilon to the k plus negligible. And this is tight for the following reason. The first reason is that there is this counterexample where we have a four-message protocol where we can demonstrate that parallel repetition actually does not reduce soundness under plausible assumption. So three-message is the best you can hope for in general. On the other hand, the negligible loss term at the end is also inherent, also assuming some reasonable assumption, and this is shown in the work by Dodis, Jane, Moran, and Wicks in 2012. It turns out there is also something we can do for four-message protocols and beyond. And of course, you cannot just simply apply parallel repetition. You need to change the protocol before you do that. So in particular, we know that parallel repetition also works even for many message protocols if the protocol satisfies a property called partially simulatable either that or if the protocol is wrapped in a fully homomorphic encryption. So partially simulatable protocols include, of course, three-message protocol, but also public coin protocol, where every message by the verifier is just some random coins. And also more generally, or I should say another case is random terminating challengers, where the challenger in each round has some small probability, but not negligible probability, is going to simply accept the transcript or the interaction without any other checks. So it was shown in these works that if the protocol satisfies one of these conditions, then parallel repetition also decreases soundness. What this tells us is that we can actually take any, let's say, any R-round protocol for any polynomial R, and then we can pre-process this protocol so that it becomes either random terminating or wrapped in an FHE. Then we can do parallel repetition to actually amplify its security. And doing so will incur, before doing the parallel repetition, a multiplicative loss of order roughly R, which is the number of rounds, or lambda, which is security parameter in efficiency. And it is also shown that these laws are tied for each approach that you will take. Okay, so that concludes the classical landscape. Now let's turn to quantum. So the natural question to ask is, what happens quantumly? So before discussing quantum, let me first formalize what do I mean by a quantum security game. So in particular, we are going to consider two flavors of quantum security game. The first flavor is called post-quantum security game, which aims to capture the scenario you encounter in post-quantum cryptography, where we want to secure existing cryptography against quantum adversaries. But more generally, we can also consider quantum security games, which arise in quantum cryptography. Here, both the adversary and the challenger could be quantum, whereas in the post-quantum security game, the challenger is still classical. So as you can see, post-quantum cryptography or post-quantum security game is a subset or a special case of general quantum security games. So now let me tell you about our quantum efficient parallel repetition theorem. In this work, we proved that take any three-message quantum protocol with computational security epsilon. If you take a k-fold parallel repetition, then the security will decrease exponentially. In particular, you'll get this expression epsilon to the k plus negligible, which is exactly what you get classically. And we also show that we can adapt the suitable classical lower bound and upgrade them to the post-quantum version, and therefore this security bound that we show here is also tight. So more specifically, we show that assuming suitable post-quantum version of those assumptions, parallel repetition does not work for four-message even post-quantum protocols. And similarly, assuming suitable post-quantum assumptions, negligible loss is also inherent even for post-quantum protocols. Similar to classically, here we also show a suitable compiler where you can compile protocols so that the three-message parallel repetition applies. In particular, we show a round collapse theorem where we are able to compile any protocol down to three message in a way that preserves computational security along with other desirable properties such as efficiency. I should point out that this transformation is actually the exact same transformation that you do for quantum interactive proofs, or in other words, quantum interactive protocol with statistical soundness. And this was already shown 20 years ago, and our contribution here is to show that there is an efficient reduction so that this also works for computational soundness. The loss here is slightly worse than what you have classically, but we leave further improving the efficiency to future work. Before telling you about how we prove this, let me first tell you a little bit about the applications we can achieve with our parallel repetition theorems. So the first application is that we are able to prove a quantum analog of Yale's XOR lemma. So a Yale's XOR lemma is essentially showing the unpredictability of Boolean predicates becomes exponentially harder if you take XOR of independent instances. So here we consider a natural quantum state analog of Boolean predicate unpredictability, and we show that taking XOR also amplifies the unpredictability exponentially. We also show amplification for many quantum cryptography, and this is through a generic template where we observe that this cryptography has a 2-message or 3-message security game, and then we can simply apply our power repetition theorem. So this includes quantum money schemes, quantum commitment scheme, EFI pairs, and also quantum succinct or non-succinct zero-knowledge arguments, and so on. Finally, I should point out that our power repetition, 3-message power repetition theorem also works for post-quantum security game. So we also get soundness amplification for any post-quantum argument system as long as 3-message, and this was not known before. Okay, so to tell you a little bit about our proof, let me start by giving you the proof, the classical proof for a baby case. In particular, the classical proof for having a 2-fold power repetition for a 2-message security game. So here we have an adversary and a challenger. So the challenger starts by sending 2 independently drawn challenges, and the adversary responds with 2 possibly correlated responses. And as before, the challenger is going to accept if both folds accept, or the adversary wins both folds. So assume for contradiction that there is a good adversary that performs pretty well. Let's say its success probability is delta square. So let's say using this notation, we say that the probability that the adversary win fold 1 and simultaneously win the fold number 2 is delta square. And our goal is to come up with a tight reduction, which means that we should come up with the adversary for a single fold whose success probability should be close to delta. So one naive hope that you may have is that maybe we can simply say that the adversary either wins fold number 1 with probability at least delta, or wins fold number 2 with probability at least delta. If that's true, then we will reach a contradiction. So skipping some of the subtleties in the proof, so this is how you actually do the proof. So again, we start by having the win success condition, which is that the probability of win 1 and win 2 is delta squared. So for a technical reason, we'll actually first perform averaging over all the second fold randomness, and then we are going to consider apply Bayes' rule and to see that this expression is in fact just the probability of the adversary winning fold number 1 conditioned on randomness R2 times the probability that the adversary wins fold number 2 conditioning on winning fold 1 and also the challenge R2. Okay, so the classical proof proceeds by considering 2 cases. So the first case is that there exists some good randomness R2 that you can fix here, such that the probability that the adversary wins fold number 1 is pretty large. So let's say at least delta. So this will give you a contradiction, and the reason is that we can come out with a reduction where we simply hardwire the R2 as the advice, and then run the adversary where the second fold is fixed to R2, and then the first fold is basically forwarding the external challenge, and this reduction will succeed with probability at least delta, which is a contradiction as we desired. As for case number 2, that's just not being in case number 1. So for any randomness for the second fold, the probability that the adversary wins the first fold is bounded by delta. What this is going to give us is that if we plug this into the equality above, we'll see that averaging over the second fold challenge, the probability of the adversary wins the second fold conditioning on winning the first fold is also pretty large. And our goal is to come up with a reduction. So it turns out there's also a way to do reduction. The high level idea is just that we are going to rejection sample the second fold message until the adversary wins the first fold. So to make this a little bit flesh out this a little bit more, what the adversary does is that it's going to randomly sample R1 and then run the adversary, and as well as forwarding the second challenge from the external challenger, and then it's going to run this over and over until the adversary is able to win the first fold. At that point, you output the second fold, a response from the adversary. If you do the math, it turns out that this works. Your success probability is exactly going to be this expression, which is at least delta, and this completes the classical proof on a high level. Okay, so before moving on to fully quantum, one naive question you may have is, can we adapt this to post-quantum already? And it turns out even doing this for post-quantum is not obvious. And the reason for this is essentially, if you look at the reduction for the second case, it involves rewinding. And unfortunately for quantum adversary, there is a notorious no rewinding law which forbids you from generally rewinding a quantum adversary. In fact, it was shown that there are quantumly unrewindable protocols that are provably unrewindable, although these protocols are contrived. So there is a protocol that was constructed relative to a quantum oracle, but there is also a standard model construction that is unrewindable, assuming quantum hardness of learning with errors. Furthermore, recently there have also been some quantum rewinding techniques that have been developed in the context for proving zero knowledge or succinct argument. We will not delve into this, but it turns out that those techniques also do not immediately apply here. So here we are going to use the technical tool of quantum singular value transform, or QSVT, in order to help us to overcome this quantum rewinding challenge. In particular, we are going to use a special case of QSVT called uniform singular value amplification. On a high level, what this procedure allows us to do is that given two operators P and Q who has the following singular value decomposition, we can approximately amplify this this operator by order 1 over lambda for all the singular values, assuming all the singular values are bounded by some constant gamma. And we can perform this amplification given that we have access to essentially black box access to P and Q. And in our proof, we show how to use uniform singular value amplification to do a version of essentially coherent post-selection. So on a high level, this corresponds to sampling some version of quantum conditional distributions, which is what the classical proof is trying to do, because the classical proof is essentially trying to sample some conditional distribution. Here we are also doing something similar to that, which is that we are going to use uniform singular value amplification to do a version of coherent post-selection. In other words, some version of sampling quantum conditional distributions. Okay, so to conclude, in this work we show an efficient 3-message parallel repetition theorem and XOR lemma. Furthermore, we also show an efficient quantum round collapse theorem and how to use it to do parallel repetition for 4-message protocol and beyond. So in this talk, I skip a lot of things that you have to refer to the paper. One thing is the full proof, including how you handle any polynomial for parallel repetition, and also the more general case of doing 3-message quantum protocols. Another thing that I gloss over is having a uniform reduction. Here I only talk about for the classical proof, I only discussed how to do the proof in a non-uniform fashion. And there are additional work that's involved in order to make the reduction uniform. So if you are interested in any of these, please take a look at the paper. That's all. Thank you.